Hello, first of all, let me show you how the kinematics of the robot were created. So here I will create it step by step, so it will be more clear for you. So this part, let's delete and make again. So here we have all revolute joints. So revolute joints we draw this way as a cylinder. So this is our first joint, this one. So this is rotate around this axis. So here, firstly, how we need to draw axis. Firstly, we start from the z-axis. So it's axis of rotation. So this part rotated this way around. So the z-axis is a rotation axis. Also, let's draw it this color, the same color. So we will see where is which axis. So this will be our first axis, Z0. Next, we draw the x-axis. So it must be perpendicular to its own z-axis and perpendicular to the z-axis of the previous frame. So here we just started, so it's our first axis. We don't have the previous one. Let's draw it also blue color. And we draw it perpendicular to the z-axis. So it will be x0. Next, we, by this rule of thumbs, can draw the y-axis. So this finger is z-axis, this finger x, and this finger will show us where is y-axis. So y-axis in this case will be this way, this y0. Next, we move to the second joint. So this one is the second one, so it's rotated this way. So we draw it somewhere here, because here we have the distance L1 and distance L2, so it has offset. Here, let's draw the second one. Again, take a look to our rules. So z-axis must be axis of rotation. So we can draw it this way or this way. So select which one we want. So this will be Z1. Next, we draw the x-axis. X must be perpendicular to this and to the previous one. For example, if we draw x this way, it's perpendicular to this one, but it's parallel to the previous one. So it should be based on the rule 2 and rule 3, x must be perpendicular to the previous one and it should intersect the previous axis. So currently they not intersect. So we cannot draw x-axis this way, so we draw it on the right or left. So this will be x1, so now it's perpendicular to the z1, and also if we continue this axis, it will intersect this one, also perpendicular to this. So these two rules are satisfied. So that's how we draw this axis correctly. Next, based on this rule, we draw the y-axis. So in this case, it will be up y1. We move to the next joint. So is this joint. So it's also rotated the similar way as this one. So we draw it similar to this, to the previous one. So also the same line, no offset, they just shifted by the distance L3. So we draw similar here, somewhere above. Again, first of all, we start from the z-axis. So again, it's axis of rotation, z2. Next, we draw the x-axis. X should be perpendicular to this one and to the previous one. For example, if we draw right side, it will be perpendicular to this, but they not intersect with the previous one. So here, if we continue this, they will not intersect. So it's look this way and that one looking for us. So they not intersect in 3D. So that's why we need to draw this axis bottom or up. Let's draw up x2. So now it's perpendicular to this one. So if we continue this x-axis, it will be also perpendicular to the previous one and intersect it. And based on this rule, we draw the y-axis. So here we draw y2. Next, we move to the next. Our joint is here. So this is our next rotated joint, and it rotates this way. So here it has this offset L4, and also it has some offset from this point. So we should draw it somewhere down. Again, we start from the z-axis. Z-axis is axis of rotation. For example, we can draw it left or right. So it's z3. Next, we draw the x-axis. So x perpendicular to this one. For example, if we draw this way, it's perpendicular, but this one is looking for us. So it's z2. Again, they not intersect. If we draw x this way, again, they will not intersect in 3D. So here we have the note. If these rules not satisfied, we need to translate axis until it hits the other. So here, for example, if we wanna draw it up, x3, then we need to shift this part to the previous axis until it hits the previous one. For example, to here, and we need to check that everything is okay. So it's perpendicular to this one, and it's also perpendicular to the Z2. So we can, for example, redraw Z2 this way, so we will see that they are perpendicular to each other. So that's how we shifted this joint. And as this part is rotated from here, it doesn't really matter from where we will rotate this part, from here or from here. It will rotate the same way, so that's why we can move it to here and nothing changes. Next, based on the next rule, we draw the y-axis. This our y3. Move to the next joint. So next is this joint, so it's rotated this way, so similar to these two. Doesn't have offset with it, so it's the same line here. For example, we draw this way here. So the same axis. Next we draw, start again from the z-axis. So this will be z4, x perpendicular to the current one and previous one. So if we draw to the right, it's perpendicular to this, but not to this. They are the same direction. So we need to draw it down or up. So this will be Z4. Not Z4. X4. So it's perpendicular to Z4. If we continue Z3, we will see that they perpendicular to each other. So this way it's correct. Next, y-axis, again based on this rule. If we locate fingers, we will see that it's this direction, y4. Next, our last joint. So this here, it rotates this way, the end effector. So end effector is similar to this joint. So this joint and this joint rotates same direction. So here we draw the end effector joint. So here we again start from the z-axis, axis of rotation, z5. Next we go to the x-axis. Again, if we draw this one, x up, perpendicular to this, but not intersect this. If we draw this way, perpendicular to this, but they parallel to each other. So again, here we need to apply this node and translate the x-axis to the previous one. So if we, for example, draw x5 here, it's perpendicular to the z5 and to the z4. Next, we also, based on this thumb rules, draw the y-axis. So it will be this direction, y5. So here was our end effector, and here we also have the drill point. So from end effector to this drill point, we also need to draw this point. So this point will be here. So again, firstly, z-axis, for example, here z6. x6 So it's perpendicular to this and to this. And y6. So this kinematic diagram we finished. Also, let's draw these distances to our diagram. So from our base to this origin, it will be distance L1. L2, again from our origin to this point, to origin of the second joint. So here we have L2. Next we have L3, distance between these two origins, between this one and this one. So origin is here. Here is L3. Next, L4 is distance between this one and this one. So here we can also see that it's pretty small, but also we need to take it into consideration. So distance between this origin and this. Here we have L4. Next we have L5. L5 here. And from here to the drill element we have L6. So next so we finished with the axis. Next let's move to the Danavid-Hartenberg table, DH table. So for DH table we will have number of rows, we will have the parameter theta, parameter alpha, parameter r, and parameter d. So theta and alpha it's rotation parameters, r and d is displacement parameters. And n is number of rows we will have. So this n is calculated as follows. So number of all our regions, so here is 1, 2, 3, 4, 5, 6, 7. So from 0 to 6, in total we have 7 regions, and formula is as follows: 7 minus 1, so it will be equal to 6. So here we will have 6 rows. 3, 4, 5, 6. Let's start from the theta. So it's rotation around z-axis to match the previous x-axis with the current x-axis. So first one we have just the beginning here. So here we nothing to compare x with. So here we will have 0 rotation, but also rotation can change later to any angle of theta. So here we write just the angle theta, what we may have later. not here, but here for the first one origin. Next one, here we need to match previous x with the current x. So here, if we take a look at this, so this x and this x is the same direction here. So distance between them we cannot rotate, so as they are the same direction, so here we also write theta. So this angle can be changed later to theta. Next, let's take a look to this origin x1 and this origin x2. So they are different direction. So here we need to rotate around z, the previous z, the current z is z1, previous z is z1. So here current z2, previous z1. So we need to match the previous x-axis with the current x-axis. So for example, if I redraw x1 here, we need to rotate around z1 to match these two. So, and rotate we need counterclockwise, so this direction. So distance between them will be 90 degrees. So here we write theta plus 90 degrees. The x3, x2, x3 is the same direction, so here we'll write just theta. x3, x4, the same direction, also theta. x4, x5. Oh, sorry. Let's make this part again. So here we take a look from these two first, the x0, the zero origin and the first origin. So here we need to, here we see that previous origin and current origin, they the same direction. So again, forget what was before. So here these two same directions, so here we just write theta. Next we take a look to the x1, x2. So here the rotation will be around z1 axis, again 90 degrees. To match them, x1 and x2. So here will be theta plus 90. Next, x2, x3, same direction. Here just theta. x3, x4, same direction, theta. x4, x5, same direction, theta. And last one, x5, x6, also same direction, just theta. Next we see what is alpha. So it's rotation around current x-axis to match the previous z with the current z. So again, firstly, we take a look at these two, zero and first origin. So we need to rotate now around current x, which is x1, to match the previous z with the current z. So if we redraw z0 here, again we take a look from here and rotate counterclockwise to match these two. So it will be 90 degrees. Here we write 90. Next, we take a look to Z1, Z2, they are the same direction. So here we will just write 0, because Z1, Z2, the same direction. Next, take a look to the Z2, Z3. So we rotate around X3, so we can redraw Z2 here. Take a look from X3. So we take a look from here to match these two. Rotate counterclockwise, so it will be 90 degrees here to match these two. Here again 90. Next we take a look to the Z3, Z4. Here we rotate around current x-axis, which is x4. So Z3 we can redraw this way, Z3. So we take a look from here and rotate counterclockwise. So it will be 270 degrees in this case. Next, Z4, Z5. Take a look from X5 to match these two counterclockwise. It will be 90 degrees. Here we have 90. And here Z5, Z6, same direction, so we write 0. Next, R. Distance between previous and current origin along the current axis. So here along current axis is x1 and distance between previous and this one is L1. Here we draw L1. Next we have the first one and the second one. Here we have, so here is important that we need to take a look to along the current x-axis. So between x1 and these two, current is x2. So we take a look from this direction, distance between these two. So it will be distance L3. L3. Next, we take a look from these two, x2, x3. So current is x3, and it looks up. And distance between these two, looking down. So here we write minus L4. Because origin x-axis is up. So that's why here we write with a minus. Next, x3, x4. So we're just looking up, nothing changes here, 0. x4, x5, also nothing changed, 0. x5, x6 also up, so also 0. Distance not changed this direction. Next, D. Distance between previous origin, current origin along the previous z-axis. So here, previous axis, current axis. So here we take a look distance between these two along the previous z-axis. So this distance will be L2. Next, here Z1 is to the front direction. So here it's not changed, 0. Here Z2 also front direction, 0. Here we have Z3. And between these two origins we have distance L5. Next, Z4 looking for us. So here we don't have any distance, 0. And between Z5, Z6 we have this distance L6. So that's how we finished the DH table. Next, let's see how we calculate the inverse kinematics. So here we have our robot, 6 rotation joints of it, and here we So here we have the known point which we want our robot to come. So in worst kinematics, we know here the position, rotation of this point. So we want our robot to come to this position. So this part is known for us. So this matrix is known. So this matrix T. And this point is also important. So here we have, so why this point is important? Because this point depends, the position of this point also only depends on the previous three joints here. And this first one, second one, third one. So we can draw example this way. So it will be 0 R 036. Let me take a look how I 03. Here will be, let's draw T 03. Here we draw T36. So why this point is important? Let's take a look at this example with Unity. Let me hide this end vector. Okay, we'll currently just hide this part. So we're interested in this point. So let's take a look to this point here. So what will change its position? So here we have the robot, so we can change, for example, this position. We write this robot. So this will change the position, the first joint. So the position of this point will be changed by the first joint of this point. So the first joint changed this position. This also, the second joint also changed the position. So this point position also changed with the second joint. Joint 3 also changed this position. So position also changed. Next, let's take a look to the J3. So J3 don't change this position, it only change its rotation. So here position the same, but rotation is different. If we take a look to this, it also changed the rotation of the final point, but don't change its position. And this one, the last angle, the end effector rotation also don't change this point position, but also change the rotation. So here you can see that this one changed position, this one change this position of this point. This change position, but other joints just change its orientation, don't change position. So position is the same. So this one also don't change position. So position stays the same. So that's why here we take it into consideration when we calculate inverse kinematics. So this point position depends on previous three joints, and next three joints just change orientation. So that's why we can firstly bring the inverse kinematic calculation to the two parts. So firstly we calculate the first three joints. So that's why we draw here only first three joints, and here we have the ZC. So this point has coordinates XC, YC, ZC. So it's this point. Here we have the given coordinates. They here, so coordinates, they were here all X or Y or Z. X, Y, O, Z. So it's these coordinates. So this coordinate is given for us, and also rotation here is given to us. So example, we have some object which is rotated, so we know its rotation, so we know how the gripper should come to it. So this point and this point, the difference between them is this distance d6. So d6 in our case is L6. So L6 from this point to this point is L6. So that's why in order to calculate this, we want to calculate this part is here also we can draw. So it's transformation matrix. Also here we will just have rotation matrix. He is R. He is R36. So in order to find this point XC, YC, ZC from here, because this one is looking down, so that's why we need to take minus here. So this one will be this one minus this and multiply to the rotation matrix coordinates. So how this part is rotated, so here we apply rotation matrix for it. Because maybe it will be, for example, this direction, so it will be rotated this way. So it will be also known for us because this point rotation we know. So here we multiply, for example, if it's just goes down, so here we will have the rotation. So for example, here we have the axis X, so that down, and Y somewhere here. So if we only have this configuration, so here will be just the Z displacement, because X, Y don't change, only changing is X. So this part for this configuration will be 0, 0, and here minus L6. Just for this configuration. For our robot, we have different configuration, so we need to take it also to consideration. So just a particular case. So that's how we calculate this point XC, YC, ZC. So next we will have this point here. So this point has coordinates ZC, YC, XC. So that's the point we found, is this point. So here we have three joints and this part. So same as we drawn before, L1, L2, L3, L4, and L5. L1, L2, L3, L4, L5. So we just redraw this without last three joints. So these last three joints only make rotation and don't change this point as we saw before. So what we do next here? So here, first of all, we can find the theta 1. Theta 1 is how the first joint rotated. So here we have the value YC. This one is XC. So we can find this angle as a tan of this YC. So YC is this distance to the XC, this distance. So theta 1 is the easiest one to find. Next, here based on the robot configuration, we may have the different inverse kinematic calculation. For example, the calculation I used with Visual Studio, it was the first calculation. So let's take a look to the robot configuration. So when we, for example, click calculate kinematics, we will see that robot will have this configuration. So its configuration similar to the first case. So when this one goes down and this one goes up, here it's different configuration. So this one will go, this one is the first one. Let me draw to you. So this configuration is first one. If we would have the second one, the joints would be located this way. So this one is the second one, and this one is the first one. So same to this. So the calculation I applied to the program is the first one. So I mark it here. So once we found theta 1, we can move to the calculation of theta 3. So theta 3 here is this angle. So we redraw this part. So just redraw this part to calculate theta 3 and later theta 2. So it's the same part. So theta 2 is here. This one L3, L4, L5. So just redraw this part. Also, what else we have here? So this point we know is ZC. Here we also marked the distance S. So it's distance between this joint to the last point. And here also we have the R distance. This is the R distance. Next, let's see. Also, I added here some additional distances. So this one is the A distance. So A will be, so here we consider this triangle. So A will be as calculated by the rule of triangle. So L4 square plus L5 square and square root from it. So it's just the theorem of this triangle. Next, we calculate R. Let's see what is R here. So R is this distance. So firstly, we can take into consideration this triangle. So here we know its parameters. So here R will be calculated as x square plus y square. So x square and y square will be this distance. Also, to find the r, we need to minus L1. So minus L1, so this will be r. Next, see what is S. S is this point minus L2. So this point minus this will give us this. This is S. Well, next we also have B. So for B we consider, for example, this triangle. So this is R and this one is S. So R square plus S square, square root from it. Next we find cosine phi. For cosine phi we consider this triangle. So here we know everything B, A, L, 3. So we know all sides of this triangle. So we can find phi by this formula. L square plus A square and minus the front side B over 2 multiply L3 multiply A. Here just I make a replacement, so this will be equal to D. And phi will be equal to r cosinus of D. Next we also have the beta angle. Beta angle is this one. So for example, phi to here. So this is phi and here we have beta. So phi plus beta is 180 degrees because here straight line. So beta will be equal to 180 minus phi. Next we have also alpha angle. So alpha angle is this one. If we draw it to rectangular, we also will have the alpha angle here. So this and this are alpha angle. So this one, this one. So alpha we can find to consider this triangle. So it will be tangents L4 over L5. So this is our alpha. Next, let's see what is Q3. So here it will be beta plus alpha and plus 90. So here theta 3 is this angle. So firstly we have the straight line configuration. So here, for example, if we have 0 theta 3 angle, it will look this way. If we rotate it, we will have the theta 3 angle. So theta 3 angle is this angle. So also we can see here what is theta 3 angle. So how we rotate it. So this is theta 3. So this is also theta 3. Here theta 3. From here how we rotate it. So theta 3 will be beta plus alpha and plus 90 degrees. Now let's see why we here at 90 degrees. So if you take a look to this configuration we draw, it's a bit different to this one, because here we located this joint here. So we located this joint here and then we moved it up. So its configuration a bit different from what we draw before. So its configuration similar to this. So if we again draw every axis, redraw it this way and make the H table, we will see that here for the joint number 3 we need to add 90 degrees. So that's why here we also add 90 degrees to it, just based on the table we created. So this configuration pretty similar, but here will be final result. If we calculate this, it will be beta minus alpha plus 90. Just sign is different. Next, let's see how to calculate theta 2. So theta 2 is here. First of all, we will find phi 2. For phi 2 we take into consideration this triangle. So this side is S, this side is R. So phi 2 will be equal a arctangent S over R. Next we find cosine phi 1. So phi 1 is here. So again we take into consideration this triangle. Oh, what is it? So here to find phi 1 we need to take this sides L3 square b plus b square and minus opposite side a square over 2 multiply L3 multiply b, so it will be d1. Next, phi 1 will be our cosinus of d1. So theta 2 is this one. It will be phi 2 minus phi 1. So pretty simple how to find theta 2. So for different configuration here will be different sign. Next, let's see how to find theta 4, theta 5, theta 6. So previously we created the DH table. Let's copy this to here. And let's copy notes. What does it mean? Every parameter. So before we define the parameters, the rotation parameters. So this is rotation and this one is distance. So we have two rotation parameters. So here we consider the two rotation metrics, this one and this one. And we have two distance parameters. So we have this distance, this distance. For distance, firstly, we also consider it d1. Here, if we take a look to d, it corresponds to the z-axis. So this one is x, this one is y, this one is z. So d is what's the distance between z-axis. So here we consider the z-axis. and here just the rotation matrix. So here the translation parameters t, and this one the rotation matrix. 111 means identity matrix. Here 1 0 0 0 1 0 0 0 1. This identity matrix. Matrix means, so it's equal to no rotation. No rotation, just to write it in matrix form. Also, let's take a look to the R. R was the x-axis, so that's why here we have R here, put here, so this one. Why is that? Next, we take a look to rotation matrix. So theta was rotation around z-axis. So here rotation around z, and that's how the rotation matrix of z-axis looks like. So here on the right we also have some formula how the rotation matrix for each axis looks like. So for rotation around z it looks this way. So that's why we put it here. And here we have no displacement and just rotation matrix, again to write it in matrix form. Next we have the rotation around x for alpha. Alpha is around x. Rotation around x is this matrix. So that's why it looks here similar. So if we multiply all this together, so this multiply this, and this, it will give us this. So we multiply with each other, so we will get this matrix. So it's transformation between every joint. So here we will just substitute the values for every joint theta 1, theta 2, theta 3, theta 4, theta 5. For example, as we considered before, so here will be distance between these two, and these two will be t01. Here will be t12, and so on. So multiply them with each other, we can find the coordinates. Here, this will be t2, 3. So if we want to find t03, which is this one, the whole one, t03 will be equal t01 multiplied by t12 multiplied by t23. So step by step we can find this point. So to find this point again, for every we need to substitute the current. For example, for first one we will put these values. So if we put these values to here, we will find the transformation. So this will be t from 0 to 1. So if we put these values to this formula, it will be from the first one to the second one, and so on. That's how we can find transformation between every joint. Next, let's see what we know and what we don't know. So this part is known for us. So this R is given by inverse kinematic task. So this R is between origin and last point. So this R is given to us. Also, here we defined theta 1, theta 2, theta 3. So previous three angles we also found. So this we can obtain by this. So, because we found theta 1, theta 2, theta 3, so this we can also calculate. So last we need to find this. So how we can find this? So we move this to this side. So it will be -1 or transposed and multiply by R. And R36 in the symbol form will look this way. Let me show you how I find it in symbolic form. How I find this formula. So for this I used the MATLAB because MATLAB can calculate it in symbolic form. So just I mentioned here that we want to calculate this, all this, 4, 5, 6, and this theta in symbolic form. So again here I used the same formula which we specified here. So I just used the rotation matrix. So this one is rotation. Here I also was interested in rotation, so I used this part. So these two are similar. So for R4, I just put here theta 4 and alpha 4. So for this formula for R5, here theta 5, alpha 5. So again, as I mentioned here, to find every, we need to take a look to specific values. And last one is this one, theta 6, alpha 6. So here, if I run this section, I will see what will be if I multiply this matrix with each other in symbolic form. So we will get this matrix. Matrix R36. So that's the same I wrote here. So C means cosine, S means sine, just to simplify it a bit. So if you take a look at this, it will be similar to this what I wrote here. So here cosine theta 4 multiply cosine theta 5 multiply cosine theta 6 minus sine theta 4 multiply sine theta 6 and so on. So that's just how I get this formula. So to multiply this with our values with theta 4, theta 5, theta 6. So it's how it's in symbolic form will look like. And here, this one we already know. So this is calculated from theta 1, theta 2, theta 3. So once we found it in symbolic form, we can take a look what is easy to calculate here. So here we just have cosine 5. So theta 5 will be equal to our cosinus of this value. Next, we take a look to these two together. Here, if we divide this over this, and it will be, so this will be removed, and this over this will be arctangents of this. So this will be just index 4. So it means the theta 4 Next, we can take a look to this tool. We can again divide it over, and it will be just the index 6. So it will be the theta 6. Again, arctangents of this over 2. So that's how we calculate inverse kinematics. Next, let's take a look to the script itself. What does it have? So here I calculated based on this position. So firstly, to calculate inverse kinematic, we need to provide the last point and how to rotate our gripper. So for this configuration, I also tested it with the MATLAB before to find the suitable configuration for our robot. So this configuration will mean that x is equal minus 90. So to make the gripper rotate this way, so we will drill forward. So just this configuration, y equals 0, z equals 0, and x we rotate minus 90 degrees. So if we again also take a look to this matrix compose rotation, it will multiply matrix with each other. So RR will be our matrix. Rotation matrix, how to rotate the gripper. So it's same to this. So it's the rotation part, and this one is translation part, x, y, z. And here how to rotate the gripper of the robot. So firstly, let's take a look to this point, how to get this point. So first of all, also I firstly adjust every joint here. Here also let me show you how to find firstly distances of the robot. So here is our start point. So we rotate from here, and we need to also firstly need to know what is L1, L2, L3, L4, L5, L6. So here we find L1, L2, L3, L4, L5, L6. Let me show you how I found these values. L1, L2, L3, L4, L5, and so on. So this one is our base point. Next one, here we will have the L1 and L2. L1 and L2. So L1 is equal 0.729, and this one is L2. Next we have the L3, distance between this and this. So it's this value. So it's this value. Next we have to define distance to this. Distance between this point and this point, this point and this point will be L5. So between this point and this point. So to find this, we need to move it to here. So this will be the L4. L4 is this distance. So this L4. And this one is L5. This distance, this distance. And last distance, so once we define this, we can move this axis back. Control Z. Last between this point and this point. So it's our end effector. So it's end effector. So for end effector, if we increase it, we will see that this point is a drill point. Also, important moment when we check this axis, they all should be the same line. So they all should be the same line here. So that's also I aligned with unity. So if we check all this, they will be the same line. Same here for configuration. Here also should be the same line. So this and this also same line. So they are just different by z-axis. Next, let's see how to get the point, how I get the point for testing. So here we have some inverse kinematic point, which we have in the space. So here we have base origin. So also we need to calculate everything from base origin. So it's same to this. And here also important that we need to, here everywhere we need to have the similar parameters. Scale parameters should be 1 for correct points and similar angles. So base origin, here I have the tested point. So it's this one, 2, 3, 2, 1, 3, 8, and 3, 0, 8, 5. So it's this point. So we calculate in kinematics based on this point. So here we have the script. So here we have the same point. So if I click calculate inverse kinematics, the robot will move to this point. Again, how can we check that we have the right point? So here we have the origin of this drill point. So this origin, so this metal part, which we also detect by sensors. So this point we calculated. For example, if I move this to here, to the base origin, we should see that here they have the same point. So this value 232, here we have also 232, here 138, here also 138, 3084, 3085. So the same point. So that's how we can check that we arrive to the correct position. Next, we can move it back. So that's how we can check that inverse kinematic was right calculated. Let's take a look to, so this means the trajectory of the robot. So when we calculated the inverse kinematic, for example, let's consider rotation. So first of all, some of our joint had this angle. For example, it was theta 1 of our start point. So it's start point. And then we calculated something like this, that robot should move to here. We'll draw another color. So it's also a new theta 1. So this desired point. So between this, it should move to this position. So our robot. So here just inverse kinematic point, and we also need to calculate the trajectory. So trajectory here calculated as follows. This orange theta 1 minus blue 1 theta 1 and divided over 40. Then trajectory will be equal this our start theta 1 plus this part. So here it just calculated linear trajectory. So this will means linear trajectory. So linear trajectory just applied here to the previous angle, to the initial angle, we add these discrete steps to the robot. So this is this formula. Initial, the desired minus initial over the steps, how many steps we want to make. Next, let's see this calculation. So this is just what is given for us. That's how we calculate xc, y, c, z, c. Same formulas. So same formulas as here. Xc, y, c, z, c. Next, theta 1. Pretty easy. So theta 1 similar to this. Next, we calculate theta 3. So we have similar formulas here for theta 3. Also for theta 2 have similar formulas. So theta 3, again we can see that beta plus alpha plus 90. Theta 3, and theta 2, phi 2 minus phi 1, same formulas. Next we find theta 4, theta 5, theta 6. So here we need to consider what we found before. So alpha is known by our table. It is known by this table. So alpha 1 90, alpha 2 0, alpha 3 90. Next we have this. R1 is equal L1, also based on our table. R1 is L1, R2 L3, R3 minus L4, and similar for D. D1 L2, D2 0, and D3 0. Also here we use the theta angles we found before and alpha angles. So again here we use this formula. So this T1 is similar to this one. So it's exactly the same. So next we multiply these three with each other and find the rotation matrix from it. So that's how we found this rotation matrix. So as I told you, this is known, so it's this one. So based on what we found before, we found R03. Next, we need to apply this formula. So it will be this one, this part. So that's how we find R36. So this R is also known for us. That's how we want to rotate the end effector. And from here, based on the formulas we explained before, we find theta 4, theta 5, theta 6 with the same formulas. So once we found all this, we calculate the trajectory. So here we just calculated inverse kinematics and this part to calculate trajectory. So these are our angles. Now some initial, and here the desired, so desired minus initial. Let's start this one again. So here we have initial angles. So this by default are initial angles. This is initial, and this angle what we just found with inverse kinematics. So we do this difference between these two angles to calculate the linear trajectory. And we start this coroutine, which is called loop with delay. So here we apply this trajectory to our robot and modify its angles. So here we, during how many iterations we have, so here we currently have 40. So we update step by step in this loop our robot angles. So these robot script angles will be updated based on the trajectory we calculated. And here, how fast we want to change. So here's a delay between every position. So if we increase it, it will be more slow. If we decrease it, it will be more fast. So here modifications of our robot. And here some functions to move robot to initial position.